In this problem, we have a robotic arm that consists of two links, OA and AB, pin connected at A as shown. Mass of each link is shown, and each link can be treated as a slender rod. If we wish to accelerate link AB from rest so that it has an acceleration of 3 radians per second squared while keeping the left link stationary, what moments should we exert at joints O and A? This motion occurs in a horizontal plane, so when I draw the free body diagram of the links, I won't show any weight on those diagrams. So let's begin by drawing a free body diagram for the left link OA. Let's say this is the left link OA, and I'll show, let's see, pin at O has 2 pin reactions, so I'll show 2 forces, one horizontal, one vertical. I choose to name them OY and OX. At the right end of it, point A, I have again 2 pin reactions, but observe that we're interested in finding the moments to be applied to joints O and A, so I will also show a moment MO at this left end and another moment MA at the left end, and I choose to show 2 pin reactions at point A. I choose to draw them left and down. These are unknown forces, so I can choose to draw them in any direction I wish as long as they are unknown. Let's call this AY. Let's call this force AX. Length of this rod is 0.6 meters. So that's what I want to show for the left link. For the right link, let's draw this to represent the link AB. Since they are connected at point A, I should show the reaction forces as pairs of action and reaction. So if on the left link AX is shown to the left, on the right link I want to show it to the right. So let this be AX on the right link, and I show AY up, AY, and let's see, I want to show a moment MA on the right link. I showed it clockwise on the left one, so action and reaction. Here I should show it counterclockwise, so I show MA on the right link like this. Then this is point B. There is no force at point B, but this link has a center that I designate by letter C. Since link AB has a rotational motion, its mass center is going to have an acceleration, a linear acceleration in this direction and another one in this direction. So this is AY. Let's see, this is MAY, this is MAX. So this is what I want to show on the free body diagram, and observe that link AB is also rotating, therefore I should also show an angular load I alpha. So here I'm not showing a separate mass acceleration diagram, I'm showing the inertia vectors, mass times acceleration, on the same free body diagram for simplicity. So let's begin by writing equations of kinematics. Kinematics of link AB. Kinematics of AB. Observe that AB has rotational motion about point A. Therefore, mass center C has an acceleration AX, which is R omega initial squared. But since this started from rest, initial speed omega is 0, therefore AX turns out to be 0. AY equals to R alpha. R is radius of rotation, which is distance from A to C, or half of 0.5, which is 0.25, the distance between A and C. So I multiply 0.25 times alpha, which is 3. This gives the acceleration of 0.75 meters per second squared. So let's continue with kinetics of link AB. Kinetics of link AB. I write equations of motion. Let's begin with net force in x direction for link AB. The only force I have in horizontal direction is A sub x equal to MAX, but AX is 0, therefore this force is 0. So this unknown is found. On this corner I will write kinetics of the left link OA, which is stationary. Net force in x direction for link OA is 0, but the forces that I have shown on the free body diagram of the left link are OX plus AX, which is 0. This means that OX, which is equal to AX, and they are both 0. So these are the horizontal forces. Now, let's continue with the Y equation. The Y equation for link AB, net force, to have more room, I'll move to the left right here. Net force in Y direction equals to MAY for link AB. If you look at free body diagram of link AB, we have the following forces. AY going up, that's the only vertical force, equals to MAY. M is 7 kilograms. AY is, let's see, 0.75. So this gives me a force for AY equal to 5¼ newtons. So that's another unknown. The next equation for link AB is the moment equation. So I write the moment equation, net moment about center C equal to I alpha for link AB. Recall that I, mass moment of inertia for a slender rod, is 1/2 of ml squared. So if I write the moment equation for link AB, the right link, I already have vector MA, or moment MA I should say. That's one load. I'm summing moments, so AY has a moment about center C, but its rotation is clockwise, therefore its moment is negative. 0.25 is the distance. The force is 5¼ we just found it a moment ago. And then that's all I have, equal to I alpha. I is 1/12 of M, which is 7L. Length L is 0.5 squared, and alpha is 3. So we can solve this equation for MA and get a numerical value of 1.75 Newton meters. So this is one of the unknowns that we initially were after. This is one of the unknowns that the problem asked for, and since it is positive, that means the moment that should be applied to joint O must be in counterclockwise direction. To finish, we want to go after the last unknown M sub O. So if I look at free body diagram of link OA, the left free body diagram, and write the moment equation, I choose to write moment equation about point O. So net moment about point O is 0 since link OA is stationary. I choose counterclockwise to be positive. So this gives me MO plus the only other thing that has a moment about point O is AY, which is clockwise. So I should write minus 0.6 times AY, and we found it to be 5 1/4. And then we have vector MA, which is clockwise. That's already a moment. I don't want to multiply it by anything. So I write minus 1.75 equal to 0. Solving this equation will give us MO. It turns out to be 9.7, 4.9 Newton meters. It's positive, meaning the moment applied at joint O should also be counterclockwise. Thank you for watching.